Good afternoon, Prof. My name is Arif, and together with me are my group members Huijie, Rensan, Yuanwei, and Sharon. Today, we will be presenting to you on our implementation on an improved bully algorithm which make distributed system architecture a more efficient one. So to start off, this is the table of content for our today's presentation. Firstly, we'll be going through the system design and the current situation and problems, next our approach to these current problems, and the overall system flow, and then the solutions that we are about to implement, and then lastly, the implementation demo. So firstly, the overall design of our system aims to create a flexible and more effective distributed system and at the same time cater for the major common issues like sudden spike in the incoming request message and also to ensure resources are equally distributed among the nodes in the architecture. So what are the current common issues that our team would like to resolve? So a very applicable example will be during the COVID period, home-based learning are being enforced where students will have to complete their daily tasks on their school LMS website. So due to the amount of user logging in onto the website at the same time, this actually result in a sharp increase of requests to the server hosting hosting the LMS, hence resulting in a potential network congestion where some of the client requests won't be interpreted by the server itself. And next, due to the increase of the user base, it will also lead to overloading of the workload on a particular server if the workload are not properly or equally distributed among the servers or nodes in the network itself. So in a more severe scenario where the entire requests are only managed by one server, this will actually result into in a single point of failure where there's no backup server processing the client request if this main server actually crashes or is not working. So as such, we are working to improve server durability and efficiency for increased workload such as home-based learning during COVID-19. Next, I will pass my time to Rensa, who will explain more about the solution and our approach. Thank you.
Thank you, Arif. So, our approach to improving distributed system efficiency and durability, which is our problem statement as mentioned by Arif earlier, will be through focusing on two main aspects of a distributed system environment, namely the load balancing and the leader election. So these are existing technology that already have multiple algorithms for them, and our team determined that certain algorithms can be improved upon to further enhance their performance. The algorithms we have chose to focus on is the round-robin algorithm for load balancing, as well as the Bully algorithm for leader election. So my teammates will be sharing more about the specifics of our improvement later on, and I will first be sharing about our system architecture flow. So due to our team's limited resources, our project will be implemented in an emulated, our distributed system will be implemented in an emulated Docker container environment, as we do not have the resources to set up a working distributed server system. And our system will be implemented mainly using Java RMI. So in a distributed system, there will be multiple servers. And when there is multiple servers, a coordinator must be chosen from the server cluster in order for there to be a point of contact for the client to connect to. And that is where the leader election will come into play, which is our Bully algorithm. So through the Bully algorithm, a coordinator will be chosen in the server cluster, and this coordinator will then also work as our load balancer for the distributed system. So what the load balancer will do is it will employ the round robin algorithm to distribute the client request loads and distribute the request across the distributed system. So I will now pass my time to my teammate Sharon, who will be sharing more about the specifics of our improvement to the round robin algorithm for load balancing and the Bully algorithm for leader election.
I will be talking about the use of load balancer, this round-robin algorithm that we use in our system implementation. Load balancer is basically what is going to distribute the incoming traffic requests to the network by efficiently distributing them across the multiple servers. So this way, the server can have a central location on where they can get the request from. As you can see from this diagram, the load balancer is going to sit between the client and the group of multiple servers. Round robin is then used to decide which server is going to take in the next incoming request in rotation manner that is in the load balancer. For instance, if we're going to have 3 servers, the first client request goes to the first server, the second client request goes to the second server, and so on. The load balancing is also used for the fault tolerance implementation that uses checkpointing, which saves the object file to directory that was bound to run on the VM Docker. If any failure kills a task, it can be restarted from the last entry. This is then preventing the first node from overloading each time when the system crashes. We also use multi-threading to prop the coordinator and at the same time it helps to handle the request received from the coordinator. This actually helps to prevent the queuing of unnecessary requests where it might affect the timing of the request received from the client. However, the problem of a single point of failure still remains by using the load balancer in the distributed system. To solve this problem, leader election is implemented with improved Boolean algorithm to decrease the number of exchange messages between nodes by dividing them into two groups known as the odd and even grouping to limit the number of nodes involved. I will pass my time to Yanwei to talk about the odd and even grouping algorithm in depth in the next few slides.
Now I'll go through the odd and even algorithm. This algorithm splits the nodes into two groups, odd and even, as the name suggests. A term variable will then decide which groups is going to be the candidates and which group will not be the candidates. So if the next term is even, the candidates will be 2, 4, 6, and 8. This term variable will then rotate to ensure that both groups are being used. The first scenario shows the detection by a candidate. So in this network, node 8 is the coordinator and it has just crashed. And since node 8 is even, the current term is even, and the next term will be odd. So the candidates are 1, 3, 5, and 7. Suppose that node 3 detects the failure and it is a candidate. It starts the election by following the normal Boolean algorithm, except to only candidates. So this means 5 and 7. After node 3 has sent these messages, it waits for a reply. Any reply will suffice for node 3 to withdraw from the election. Then node 5 and 7 starts their own election, and the only one who didn't have a reply will be elected. Then node 7 will set the current term to odd and announce itself with the term and the updated list of nodes. Now what happens if a non-candidate detects the failure? We assume the same condition as before, that is node 8 has crashed, but this time it is node 4 that detects the failure. And since node 4 is even, it is part of the non-candidate group. It will first multicast to all of the candidates that are 1, 3, 5, and 7. Node 4 will then wait for reply and withdraw itself from the election. So after this successful message has been sent to the candidates will then start their own election among themselves and get their replies, and the one without the reply will be elected as the leader. So what if all candidates fail? In this case, the multicast before comes in handy. Now imagine this scenario when 1, 3, 5, and 7 and 8 have all crashed and node 4 detects the failure. The multicast before ensures that it is safe for node 4 to take over, and there will be no conflicts if node 4 were to start its own election. So node 4 knows that it's safe for itself to start the election, and it starts an election among the non-candidates, get its reply, and the one without the reply becomes the leader. And that's it for the odd and even algorithm.
Hello, I'm Vijay, and I will be talking about the implementation of our system. We will be using Docker to simulate the system. So our operating system of the computer will be Ubuntu, version number 20.04.2. So within the Docker, we'll be using the by-mount function where the file will be sharing from the local computer to the Docker computer. A file will be saved into the local computer, and when the system crashes or when a new load balancer is taking over, the load balancer will read the file and carry on from the last point that the previous load balancer has stopped. Here is a few commands that we will be using. Firstly, the loading of file image. Second, listing of all available Docker container. Thirdly, listing of all image. Fourth, the by-mount function that will bind the local computer to the Docker computer. Fifth, running the existing container. And lastly, copying of the folder. So, unlike the Windows operating system, Ubuntu has its own set of RMI registry commands to start with. So these are the three main functions or commands that we'll be using. Right now, I'll be showing you our demo. I'll be showing you the demonstration of our system. Here is a list of execution files for you to try it on. The list of execution files consists of all the commands that we are supposed to key inside the command prompt. So upon clicking on this script, you'll immediately create the RMI registry as well as helping you to compile the whole system. So let's start by creating our server. Here are two options for you to try out our bully. Since this is a local computer, we'll use the normal bully. Upon success, it will show server started. So there are 4 options for you to choose. The local computer indicates that only the local computer can use and not on the Docker computer. That's because there's a ready-made GUI for you to test it on the local computer. And upon success, you'll see a GUI that is ready-made for you. The username will be test and password will be pass123. Upon success, you'll see the login of the user. I will be showing you the Docker portion. So the image will be provided to you. And then firstly, create a folder. After creating the folder, run the bind mount function that was shown in the presentation. So after running the function, the container will be created immediately for you. So our location will be at home/CSC3004 distributed system assignment. So over here we have the list. We will have our source code and the executed script. As you can see, there are 2 executed scripts that is ready made for you. So let's run by a server first. So upon success, you'll see that the server has started and a folder will be created in the local computer. As mentioned in the presentation, this is the file that will be saving the last checkpoint or the recovery file for the load balancer. Now I'll be demonstrating our normal boolean. So similarly, run the executed script. As our topology is a peer-to-peer topology, first, since we have created a server, we will be using the client to connect to the server. Upon success, the election will be started, and since 3 is the highest ID, 3 will be elected as the leader. So, upon creating the client, we will use 3 and 4 to simulate the boolean. So first, we will be using the normal boolean, and the IP address will be bind to the leader. There will be a number of requests for you to simulate. So for instance, let me key in the number 10. 10 requests will be simulated as the user is trying to log in. As you can see over here, the load balancer, which is the leader, will be transmitting the request to the other nodes. So I will be demonstrating the improved version. So as you can see, the current node that is available is 6, and the update term is 0. As mentioned, 0 will indicate that the current election will be only taking the node that are even, and if it's 1, you'll be taking the nodes that are odd. So I will be connecting all these nodes to the system. So right now, I'm going to crash the leader node. Upon crashing, the election will begin, and after probing, all the nodes realize that 6 is dead. So the election, since it was in the even, the next election that begin will be currently taking the odd number, which is why the current term is 1 and the elected leader is 5, and it is electing between 3 and 5. As shown in 3 has started the election. After knowing that 5 is the biggest ID, he will announce to 2, 3, 4, 5, and 6 that 6 crashed. He will update the list, and 6 will be taken away from the connected node. And if 6 try to rejoin, 6 will become the highest ID and you will become the leader once again. So after restarting the RMI registry, I'll be connecting to 5. So as you can see, the current term is updated and 6 is now the leader because he has the highest ID. So thank you for watching.